tour. The next presentation we have is about seawater carbonate biogeochemistry and will be presented by Professor Patrick Martin from the Asian School of the Environment at the Nanyang Technological University in Singapore. Professor Martin is a marine biogeochemist studying total carbon and nutrient cycling. Professor Martin, please.
All right, thank you very much. I can already, the benefit of talking here on the island is I get a nice big satisfying pointer stick. So welcome everybody. You can see there will be some interactive questions, but the codes will also come up later on. Okay, so I was asked to give a talk as an overview of the seawater carbonate chemistry, just to make sure that everybody is kind of on the same page before we then move on into doing the practical work after lunch. Okay, has everybody scanned and got the Wi-Fi? Then I'll move on. Okay. So as an outline, I'll be walking us a bit through why we want to look at the carbonate system. We'll be looking at the basics of that. And then I decided, instead of torturing you with a lot of chemical details, I've tried to make it not too esoteric, but also think a bit more about the practical considerations for sampling and measurement. And one thing I want to highlight at the end is that we do need to be careful about the fact that there are different pH scales. Okay. Now, the first question has already come up, I think. So a bunch of you have already responded. You can still go through, I think. So this is pretty much what I was expecting, that we've got quite a wide range of different expertise. So for those of you who are down here in categories 3 and 4, please bear with me while I talk through things that are very familiar to you. And do feel free to provide comments afterwards. Okay, so what I'm presenting here does also reflect my own experience of carbonate system measurements here in the areas of Southeast Asia that we're studying. And hopefully for you up here in category 1, it's not going to be too painful. Okay, now the next thing that I want to ask you on is, can you give me a bit of a response about what interests you about the carbonate system? And if you're doing any measurements of carbonate system chemistry or want to be doing any measurements, just if you can tell us uh, what kind of parameters you're already measuring. So if you're measuring alkalinity or pH, you can uh, put that in. Let's see, hopefully this word cloud comes up. Um, okay. I'll give you a couple more seconds to. I think anybody online is also able to respond to this. So um, okay. I think we're getting uh, towards some stable results. pH, of course, is coming out in a big way, and ocean acidification. Um, I also think there's more to the carbon system than just that. So, we can learn quite a lot about the biogeochemistry of the marine environment in general from measuring carbonate system parameters. And of course, this goes all the way through from understanding ocean acidification through to here, like somebody's talking about carbon subduction and kind of more global scale oceanographic processes. Okay, and in terms of measurements, pH is clearly the big one that's coming out here, and then DIC, alkalinity, pH, and TA here and there. Okay, so I'll move on, but this is it gives us, I think, a really nice spread and basis for moving on. Okay, so obviously ocean acidification is a major motivation for studying the carbonate system. Um, but then in general, I think we also need more ocean CO2 data to track the ocean CO2 sink, and that's in particular the case in coastal and in tropical environments. Um, and now, when we get into coastal waters, and this was already something that was highlighted yesterday, the carbonate system can become very, very variable. So we get a lot more complexity as we get closer to shore. And that also, I think, means that we need carbonate system data at better spatial and temporal resolution to capture that variability. So what's happening here in Singapore is not the same as what's happening in the Java Sea or up in the Gulf of Thailand. Um, and I think it's really important to keep in mind here that all of these local processes are going to be interacting with the global scale ocean acidification process, because fundamentally, as we move forward into the future, open ocean waters are going to be flowing onto our shelf seas, starting off with a lower baseline of pH, higher PCO2, less buffered, and then all of this complexity of the coastal waters is going to be added on top of that. And that may then either mitigate or amplify the effect. So I think Helen already highlighted that yesterday. And aspect that I didn't put on here is that we can also, so biological productivity, for example, impacts the carbonate system quite a lot. So we can also use measurements of the carbonate system to infer something about our biology. Okay, so what is it? Right, this equation came up yesterday as well. And fundamentally, when we talk about the carbonate system, we're talking about the chemistry of dissolved CO2 and the acid-base system of seawater. Now, this breaks down into four main parameters that we can go out and measure. And handily for us, it's enough for us to measure any two of those that we want. And once we've done that, we can calculate everything else. Okay, so these are, first of all, DIC, which is the total dissolved inorganic carbon, the partial pressure of dissolved CO2, then pH being essentially the proton concentration, and then something a little bit more esoteric, which is the total alkalinity. And I'll show this afterwards. By total alkalinity, we mean the difference between all of those um, species in seawater that can accept protons and take up and react with protons, minus all of those that provide protons. Um, so if we blow up this equation a little larger, we can say the PCO2 is this dissolved stuff in here. The DIC is the sum total of all of those four. And okay, carbonic acid is too small in concentration to really matter, so it's essentially the sum of the other three. We've got some protons here, which are setting the pH. And then these two at the back here, carbonate and bicarbonate, you can see they've got a negative charge. They can react with protons. So those two additionally represent alkalinity. Okay, oh, that's great. I see a lot of excited photos, so please. Brilliant. Yes. All right, now let's see. Okay, I'll pause here. I'm happy to share the slides as well afterwards. So if anybody wants them, I can just email me and I'll send you the whole deck. Okay. Um, okay, so the alkalinity. Okay, so bear with me because this looks a whole lot worse than it is. Okay, and you do not need to memorize this. Okay, now look at the top first. That's what I just shown. Okay, so total alkalinity is the difference between those things that accept protons and those things that provide protons. And now in seawater, this essentially breaks down into the concentration of these chemicals. So the top line here is the sum of our proton acceptors. The bottom line are the things that provide protons. Okay. Now, like I say, you don't need to memorize the equation, but it's useful to have a bit of an intuitive, or start to gain a bit of an intuitive understanding of what this means. Handily, if we consider just the bicarbonate and carbonate alone, and we forget about everything else, we've already captured 96% of all the total alkalinity in seawater. And if we add just the borate concentration to that, we've already got 99%. Okay, so all of these others actually don't have too much of a practical impact. Now this means that I should go back. This means that the carbon chemistry of seawater is then really influential in what's happening with the whole carbonate system. Okay. Now here I've got another question for you. I want you to tell me, if we add dissolved CO2, so if we add more CO2 into the atmosphere that dissolves into seawater, essentially our ocean acidification, which of these four parameters will change? I'll give it a few moments. You're allowed multiple answers, so you can click every one that you think is important. Okay, so please don't just pick the one that you think is most important. Click every one that you think applies. Um, okay, good opportunity to have a sip of water. Okay. All right. Okay. Now let's have a look at this again. Okay. So if we get into okay, I'm not this isn't about giving the wrong answer, right? Um, now we can see, right? CO2 goes into seawater. Okay. We can obviously, if we've got more here, this thing is the PCO2. Okay. So certainly we expect the PCO2 to change. Okay. The dissolved CO2 is, of course, also part of the DIC pool. Okay, so DIC will also be changing. Now, when we create more of this, some of it is going to be reacting with water to give us carbonic acid, which falls apart to give us bicarbonate and the proton. So we're having an influence on the proton concentration, which means that the pH also changes. Okay, hence ocean acidification, right? Everybody, I think, got that. But now the point about TA is subtle because, so yes, you create bicarbonate, but you're also creating a proton. And remember that the alkalinity is the balance between the proton acceptors and the proton donors. So if you add one of each onto the two sides, you're not actually changing the alkalinity. You're changing the bicarbonate concentration, but the balance between the proton donors and acceptors doesn't change. So the correct answer is the other three, but total alkalinity won't be affected. Okay. Now, here's another horrible looking diagram, but it's actually quite useful to think about what happens biogeochemically when biogeochemical processes happen in the ocean. Okay, so uh, a given alkalinity and DIC we can think of as resulting in a certain equilibrium value for PCO2 and pH. Okay. Um, so what we can do is make a cross plot of alkalinity on the y-axis and DIC on the x-axis, and then we can have contours in there to tell us for any given combination of those two, what will be the resulting PCO2, which is over here, and the resulting pH. Okay, and you can see the more alkalinity we have for a given DIC. Okay, so if we're going just vertically upwards, we get to a lower PCO2 and a higher pH. And if we move horizontally across the plot, so if we add more inorganic carbon, but we're not adding alkalinity, then we get to a lower pH and a higher PCO2. Okay, so adding DIC without adding alkalinity is basically adding dissolved CO2 into seawater. So that's our ocean acidification process. Okay, so we can then look for different biogeochemical processes. We can estimate how much alkalinity and DIC is being changed, and we can then plot these on top. So if we create calcium carbonate or we dissolve calcium carbonate, we'll be moving along that particular vector. If we have photosynthesis and respiration, we're primarily changing the CO2 content, although the alkalinity will vary a little bit. And if we simply exchange CO2 with the atmosphere, that's our just changing the DIC and not affecting the alkalinity part. Okay. Right. Okay. So these arrows here show you a little bit about, this vector here is basically our calcium carbonate dissolution and formation. Okay. I think I have two more questions coming up. So first of all, if we have a coral reef growing nicely, or an oyster reef, and they're producing solid calcium carbonate that gets deposited on the seafloor, what happens with respect to atmospheric CO2? Mhm. Okay. I think the sinks are greatly outweighing the sources here, which is interesting because actually number two is correct. Okay, because and you can't sort of directly infer that from the chemical equation at the top. But if I go back a slide, okay, we can see that removing calcium carbonate is on the one hand removing DIC. So yes, the carbon concentration goes down, but you're also greatly removing alkalinity. And you need to remember that the PCO2 of the water and the pH of the water is set by the combination of those two. So if you remove DIC, but you also remove a lot of alkalinity, the remaining DIC will be pushed more towards the CO2. Okay. I don't want to dwell too much on this because it is a little bit mind-bending. So if you've got any questions about this, please feel free to come discuss afterwards. Okay. Um, oh, oh. Well, I've not had it to review, so you'll probably be fine. Um, Now, of course, on the coral reef, you've got other things going on as well. So I'm talking here only about the solid, the calcium carbonate formation. Okay. Um, Now, the next question is this: if I change the TA or the DIC by a fixed quantity, let's call it 20 micromoles per liter, will that always cause the same change in the pH and PCO2? Okay, that's really reassuring. Because if you look really carefully at my previous diagram, you'll see that depending on where you are on the plot, the contour lines for PCO2 and pH are either spaced really far apart or they're really bunched up tightly. So essentially, if you've got lots of alkalinity relative to the amount of DIC, then changing the alkalinity in DIC by a bit has fairly little impact on the pH and PCO2. But now, as we go forward with ocean acidification, what we're doing is adding more and more DIC, and we're not balancing that out with alkalinity. So anything that changes the DIC by a given quantity will then start having a bigger impact on the PCO2 and pH in the water. So things like photosynthesis, calcification, as we go forward into the future, we can start to expect larger variability as a result of those processes. Okay. Right now, the next part, the remainder of the talk is a little bit more practically oriented. Okay, because I mean, if you really want to get into the theory of all this, there's plenty of textbooks that can give you a better overview in your own time. Um, but now, Handily for us, measuring any two parameters of the carbonate system is enough. We can measure the alkalinity and DIC, we can measure the alkalinity and pH, and I think somebody was saying that that's what you're doing. Um, so I want to talk a little bit about the practicalities and contrast those a little bit. Now, DIC and alkalinity are the two that we can generally measure with the greatest accuracy. Okay, we've got extremely well-designed analytical kit that's really geared towards seawater analysis. And we can also take samples out in the field and bring them back to the lab for these analyses. Um, so generally, we can get very, very good analytical uncertainties. And these two are kind of the gold standard we can think of. Okay, so many of you who are doing carbonate system analysis would perhaps recognize that's an Apollo DIC analyzer. That's what we use. You inject a sample into it, the system injects a bit of acid, all of the DIC gets converted into CO2, gets swept into the analyzer, you get a nice peak, and then it integrates across. Okay, so it's measuring the total inorganic carbon with infrared absorption in this case. It's a very, very, very good for high accuracy measurements. Alkalinity, this is again an Apollo. Here later in the lab, you'll be seeing a different system. Essentially, you do a titration, so you start adding a bit of dilute HCl until you've removed all of those proton acceptors that are the alkalinity. Um, and the quantity of acid that you need to add gives you your alkalinity. So again, can be done ex situ in the lab, kind of comfortably in your own time. You can get very, very good accuracy on this. The problem is, of course, if you're relying on lab analysis, you tend to get lower spatial and temporal resolution because everything you have to do, you go out into the field personally, collect your sample, and bring it back. Now, pH and PCO2, in contrast, they tend to have the measurements of those tend to have larger errors, although measurement methods are improving as we go along. And these are parameters that we can measure fairly easily in the field in situ. So we can put sensors in there, and we've got some sitting out in the aquarium for you to look at, where you'll be seeing the data. Um, Probably a lot of you, pH was the biggest thing in our word cloud, so I'm sure quite a lot of you are familiar with this in some ways. Um, Now there are a few issues here. On the one hand, okay, so here's a few different pH sensors. You'll be seeing the new iSAMI later. The sensor quality varies quite a bit between these. So some will give you much better data than others. But in general, with sensors, you also have issues such as drift of the sensor, biofouling of the sensor. Sometimes it's simply a challenge to find a place where you can just deploy the thing and leave it and be confident that when you go back 2 months later, the thing's still going to be there. Um, because of currents, or somebody says, "Oh, this is an interesting looking piece of kit, I'll take that home." Um, for PCO2, similarly, we've got, so here's the one that we have on our MES Envoy. That's the photo after cleaning off all the biofouling. Half an hour before, it looked a whole lot more ugly. So that's the kind of problem that we have with sensors. So considerations here is that with PCO2 and pH, especially if you're using sensor-based measurements, you may have somewhat less or more of a challenge to get the really high accuracy data, but you can then balance that by getting much more spatial and temporal resolution. And of course, as I say, sensors are improving over time. I think there are now also some sensors available for alkalinity that can be okay. I'm seeing some enthusiastic nods there, right? So that's again, technology is advancing here. All right, so which do you want to analyze? Um, as I say, alkalinity and DIC, the benefit is they're the most accurate. You can preserve them really nicely. For pH, you can also do lab-based measurements with a spectrophotometer. That's what we'll be demonstrating later. Um, these two tend to have, PCO2 and pH tend to have higher uncertainties. And with sensors, of course, then you've got the sensor-related issues. Now, I think what you want to measure here will depend a lot on your needs, your resources, the kind of system you're in. I think it's really great to get started with some carbonate system analysis. Okay, so even if you're still trying to figure out how do we actually do these measurements, how do we make sure the data are good, start off and try and talk to others in the community. Okay, there's a lot of support around. So even if you start off with just occasional water sampling, I think especially for our region, we can get a lot of useful data from there. And if you do use sensor-based measurements, be critical of your data quality. Steve, yes. Absolutely. Thank you very much. So I think I actually will be using some of those, and I've got links to the Goan portal. I think either in the spreadsheet that's up or possibly in the slides. But yes, that's exactly the kind of example of the kind of community support you get. And there's also a wide network there of people that you can contact and get in touch with. Um, so yes, there are challenges, but there's also a lot of support. So don't be intimidated by the difficulties. Um, okay. Now there are some considerations here. So if we want to measure these, often we need really fairly good accuracy. I'll be talking a little bit about what level of accuracy you might need later, but we do need to be careful. Okay, we don't want to be collecting a whole lot of bad data. When we collect samples to analyze them back in the lab, the carbonate chemistry can change in those, okay? Any kind of biological process or calcium carbonate production dissolution will impact the final measurement. Okay, so what you measure in your sample might then not well reflect what was there in your environment when you sampled. Um, so for DIC and pH, it's really important to avoid gas exchange because either CO2 going into your sample or CO2 coming out of your sample will of course change the PCO2, the DIC, and the pH. Okay. Alkalinity, that doesn't apply. So CO2 exchange is fine. You need to make sure that your bottles are well sealed so you don't evaporate or lose water. You do need to be a little bit aware. Okay, so here for DIC pH, glass sampling bottles are great for alkalinity. Glass can sometimes, certain types of glass can leach alkalinity. So HDPE can be good. And for all of them in general, you want to avoid biological processes. Um, so, yes, Steve, here. Okay, so sampling protocols can be found online in Goan, also in the 2007 Dixon et al. Guide to Best Practices. Um, there are developments that happen. So I think there was a methods paper published, I think about 5 years ago, that was recommending sample filtration for coastal waters. And I would, in my experience, I would definitely advocate that. You do have to be careful, though, to make sure you flush out any bubbles and avoid any gas exchange. Um, you need to make sure that you seal your samples. If you need to store your samples, you should really try and consider poisoning them with mercuric chloride. That's the kind of gold standard. Now, I'll say here, and this is where I'm really keen, there are other experts who possibly even are more expert at all of these measurements than me. So in my experience, working here in Southeast Asia, in the more oligotrophic areas that we've been sampling, or sort of mesotrophic to oligotrophic, once we filtered the samples and we then refrigerate the samples, we tend to be okay for a period of a couple of weeks or so to store without poisoning them. And now this is mercuric chloride is, of course, I think, yes, 2 days ago, there was the Minamata Convention on mercury. It's really hard to move it across borders. It's not very nice to have to take it onto ships, especially if you're working on little coastal ships rather than well-equipped research vessels. So this is not easy to achieve, which is why I've said, you can find some degree of workaround, but you need to be careful. Um, any kind of deviation from the accepted protocols, you should be testing. You should be expecting reviewers to question you on that. Um, so like I say, we've done some fairly careful tests there. If you're sampling certain types of environment that are quite eutrophic or so, this really might not work well. Okay. Very happy to have any kind of input from people on that and commentary. Okay. Um, sorry? UV, can you use UV? That's a really interesting question. I think probably no, because UV will also oxidize organic matter. So then you're generating DIC. Could depend on your environment. So some of the coastal samples or some of the coastal areas we work in, I think have quite a lot of UV oxidizable organic matter. There have been, so people have, I mean, there are other alternatives to mercury, like I think benzalkonium chloride, but I don't think any of those alternatives have actually made it into the accepted ocean acidification literature. Um, I would say if, you know, try and analyze as quickly as you can. I think we did some tests where we had some poisoned samples, but we also had unpoisoned samples that we were keeping for isotope analysis. So DIC isotopes, and we then, after acidifying, we then compared DIC concentration between the poisoned and unpoisoned after, I think, 2 or 3 weeks. Steve? It does what it should. Mm. Yeah. 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 And this is, for example, where sensor-based measurements come in handy again, because if you can also have a sensor out there where you have direct measurements, you can then take your lab samples back and you can sort of essentially try to triangulate a bit and say, okay, well, with this combination of these two, I get this result. If I use the other two for the calculations, I get this result. And as long as everything is close enough to what you need it to be, then you're quite good. So I would say, all of these kind of considerations will be really context dependent on the specific environment you're working with, the particular system you're sampling, and what your needs are. So, as Steve says, right, there's Goan is a really great way to interact with people. I'm very happy for anyone to write to me. And I think Helen is enthusiastically nodding here as well. Mhm. Really? Wow, okay. Oh, okay. That would be great if you would help to disseminate that. Yeah. Mm, yeah. Steve? So I'm not going to be talking about that too much actually. I do have this aspect here, which is to, okay, here's another bit of horrible number stuff, number salad. Um, what a horrendous. Uh, so I'm not talking specifically about nutrients, but I do have something in general about the value of other measurements because they can help you understand a bit your, especially with sensors, your data quality. Um, Whether you need other measurements will depend, I think, also quite a bit on the environment. So nutrients, nitrate, phosphate and silicate chiefly, um, factor into the carbonate system calculation. So if you go back to my horrible alkalinity equation, you'll see some phosphorus and silicon in there. Um, you do need relatively high concentrations of those before they really start to have an impact. So we've measured in the measurements that we've taken around coastal Southeast Asia, silicate and phosphate concentrations have always been notably too low for this to have really any kind of meaningful impact. But then, maybe if you're sampling in a really, really eutrophic environment, if there's a lot of phosphorus discharge, perhaps that might be more relevant. The great thing is you can play around with the numbers in these kind of programs and then work out how much phosphate and silicate do I need for it to really start having an impact on the parameters that I care about. And if from that you can see that, well, I know my system never achieves those kind of concentrations, then you can not worry about it. In other cases, it can then be a handy guide to help design your sampling program. Okay, so when we've measured any two that we wanted, there's a number of ways that we can then calculate all the rest of the carbonate system. So there's an Excel macro, there's MATLAB codes, there's the ccarb package in R, which is what I use. I'm sure there must be things in Python and other ways to do it too, all kind of equivalents. But fundamentally, we have to tell the program what it is we measured. So in this case, flag 15 tells the program to expect alkalinity and DIC. We then add the alkalinity and DIC. We need to know the temperature and salinity, and we want to put in the sampling pressure. Okay. Now the pressure isn't so relevant if we're in the shelf sea because it has a fairly small impact. But if you're, I mean, Indonesia has some really deep ocean regions, so if you're getting into the Banda Sea, then that will matter. Um, and out of this, we get an awful lot of output. Okay, so we get the pH, we get the CO2 concentration, we get all of our partial pressures and fugacities of CO2, which I'm not going to go into the difference here. We get our bicarbonate and carbonate concentrations, and we get our mineral saturation states. So it's a bit of a horrendogram as well, but fundamentally it's a lot of bang for your buck from measuring any two things out of four, plus salinity, temperature, and optionally a couple of other things. Now, if you want to plan measurements or think about measurements that you're doing, I think a really important thing to think about is how much variability is there going to be in your system. Okay, so to illustrate, uh, this is a set of data that we have here from our time series measurements in the Singapore Strait. Okay, these are based on alkalinity and DIC, and then we've calculated the pH. And you can see that we get a really clear seasonal variation of about 0.15 to zero point 0.2 pH units. So comparatively, quite a lot. You can also see that that's a fairly sort of stable seasonal cycle. So within any given season, if we want to compare this season to the last season or the next season, then we've got fairly small variation. So to get the seasonality right, we don't have to be super, super accurate. But if we're trying to look at longer term developments, we really do have to watch out. Now, in contrast to that, here's a nice classic data set from the open ocean North Pacific. This is from an old paper on ocean acidification from the Hawaii Ocean Time Series. Here, compared to that, you're dealing with a seasonal cycle of less than 0.05 pH units. Okay, so it's because of this that the open ocean acidification community has extremely stringent data quality control measures, and appropriately so. Now, when we've got rather larger variability in coastal waters, that's not an excuse that allows us to be sloppy with our measurements, but it does mean that we can potentially collect useful data that might not perhaps meet quite the super stringent quality control that you might need for the open ocean. So not an excuse to be sloppy, but we can get away. We've got potentially a little bit more leeway. Although, like I say, to analyze the longer term behavior, I think that accuracy is still important. Okay, here I think we also, so this here, Steve was asking me yesterday about extreme events. So here, clearly within our time series, we have at least one, and it's one that I actually have confidence in because of all of the other measurements we took that all kind of support that. Okay. Now here's that point, right? The more things you measure, not only in the sense of if you've got a time series going, the more valuable your time series will be and the better your understanding will be, but it also provides a way of quality control. Um, so carbonate system measurements are challenging. Bad measurements will happen. They happen to us. They will happen to you. And if you've got more things measured, it can help you identify what the issue might be. Okay, was this just one bad alkalinity titration? Was this perhaps something with a faulty sensor measurement? Um, Now, we can then look, as we accumulate more and more data, we can look for coherent relationships, okay? So this is again from our Singapore data, total alkalinity against salinity, and plus minus 2 standard deviations around that. So when we get a data point that's, say, at salinity 32, and we get an alkalinity down here, we know that's really suspect, especially if the DIC is plotting within the correct DIC relationship. Okay, then maybe we can look at our PCO2 and pH sensors, and if they also tell us that we should be up here, then the problem was clearly, not wanting to call anyone out, but Malon is the one doing our alkalinity titrations. She does a fantastic job, and as have previous people before her, but we all know sometimes things go wrong either while sampling or in the lab. Um, and we can then use these kind of things to do quality control. Okay, so here's our relationship, and Malon plotted this and updated it fairly recently. This is showing you the PCO2 measured from our St. John's Island MESN buoy, plotted against the PCO2 calculated for the appropriate day and sampling time from our alkalinity and DIC measurements. Okay. Occasionally, we'll have something like this where we know the sensor was really biofouled, so we have to make allowances for that. If we chuck the known dodgy data out, we do get a fairly good. Okay, so this is RMSE plus minus 15.7. But this is across a range that we know goes from 450 up to about 650 microatmospheres. So again, that variability in coastal waters means that we can't expect this to be as tiny as it might be in an open ocean setting. Okay, oh, and the black line is the one-to-one relationship, so it's really fitting quite nicely. Okay, I think I'm getting towards the end. The thing that I want to wrap up with, because I know that a lot of people do pH measurements, And especially, we also heard from government agency representatives, for example, who do a lot of water quality monitoring. And it's important to be aware that pH isn't just always the same thing. All right? So fundamentally, we define it as minus log to base 10 of the hydrogen ion concentration. But the problem is hydrogen ions form complexes with things in water. So first of all, with water itself, as the H3O plus ion, but also with various other ions. And the different pH scales come about partly because of how pH is calibrated, also how it's actually defined. So we've got, I think there are four scales really, but the most common ones that you will encounter, I think, are these three. The first one is the so-called NBS scale, the National Bureau of Standards. So when you buy a pH buffer for use in the lab for a benchtop meter, that's an NBS calibration buffer, and I'm be wrapping up pretty soon. Now, the issue with these is that when you calibrate a glass electrode with a kind of an NBS type lab calibration buffer, um, this buffer has a very much lower ionic strength than seawater. So your electrode behaves differently in the buffer than it does in seawater. And that, first of all, there's an offset here between the scales, but it also leads to the fact that it's not there's additional uncertainties that come in from the electrode design that you can't really quantify well. So NBS data are really, I would say, less preferred. They're not the ideal way of doing measurements. And if you can, it's good to try and move away from that if you're trying to do really research level carbonate system measurements. The next one, then there's the total and the seawater scale, which are very similar. The total scale considers the protons, the H3O plus, as well as HSO4, and then the seawater scale additionally adds HF. Now, in practical terms, the seawater scale versus the total scale is a very small difference. So typically around 0.01 pH unit. Okay. But the NBS scale versus the seawater or the total scale is a really big difference of about 0.1 pH units. So when you get pH data from somewhere, it's really important to know, is this pH on the NBS scale? Is it pH on the total or seawater scale? There's the other one, I think the free scale. Okay, so those three are kind of then more similar to each other. Now, I think what really follows from this for us practically in doing more carbonate system measurements is to be aware, if you do a pH measurement, what is the scale that you're measuring on, and state your method and the scale that you're using. Okay, so if you're using something like a YSI EXO probe and you've got it calibrated against NBS buffers, just make it clear in your data that that's how it was measured and that's what the scale is that you're reporting on. And then there are ways that we can correct for that. Now, here's why I think this matters, right? This is a plot that I showed a while back. This is, you can see it was a while back because we haven't collected all the 2003 and 4 data yet. This is, again, our Singapore Straits seawater pH time series. This is what it might look like if you add even just a completely random plus minus 0.05 pH unit error on top. Okay, and errors are often not random. You've got systematic errors from having your different scales, from the pH meter being calibrated last week rather than this week. Perhaps you changed your electrode one day or another. So these errors can really start to bite surprisingly quickly, even in our systems. Okay, so in summary, I think we've looked at some of the theory of the carbonate system. We've looked at how we measure it, and I think really key, be critical of your data and be careful, try and measure as many things, and don't feel bad about flagging something as bad data. Bad data will happen to all of us, okay? Watch out for the pH scales, and then most importantly, let's network more, help and support each other across the region, write to me, write to others in the GoAN network. I just want to wrap up after this with one thing to just flash up our MESN measurement program, because I think there are some people on the live stream today who didn't see this yesterday. Okay, so we're measuring partly with our monthly boat measurements from TA and DIC, but also with sensors on the buoy. We're measuring carbonate system data. And really excitingly, okay, um, for data access, please contact us, okay? We can make these data available, especially our boat measurements. So that nice pH time series, if you write to me and agree to some terms and conditions, we can share those data with you, okay? They're under analysis at the moment, so bear with us there, but we're keen to, yeah, make things available. Okay, thank you very much. I think I'm just within a minute. Yes, thank you.
Thank you so much again for starting. Would you like to question? Agree the questions.
Okay, yes, will do. Yeah, yeah. Oh, who was I?
Go and also mentor schemes and also schemes where you can apply funding to get basic kit as well to start. There are opportunities there to try and start quite soon. So in terms of linking up with experts on longer hand through the process, but also confirming the funding and getting what's called go on in a box where you get the kit you need to then start the process.
Okay, I'll just repeat that for the online audience. So go to the GoAnd website and there's information, a kit for support, a mentor scheme for networking, some funding you can apply for to start a time series, and lots more. Woody, he was, yeah.
I'd like to ask about the spatial resolution. To what extent that we can expect different values of the coordinate systems within a given space? Let's say within a 1 kilometer square, within 1 meter square, or within 1 millimeter square.
Okay.
So how can we expect different value? I'm asking, for example, if I am about to deploy sensors, in a strait or in a plane, then how many sensors we will need to represent the actual conditions of the plane, for example?
So that's a great question. Okay, so the question is, how large is the spatial variability from kilometer down to millimeter scale? If you're trying to deploy sensors in a strait, how many do you need? And I think the answer, perhaps unfortunately, but also unsurprisingly, is it varies greatly. Okay, and I've gone back to this slide to illustrate this a little bit. So here, we don't have our neighboring countries shown here, but I think you know what the map is like, right? We've got Batam and Bintan down here and Malaysia on top. Now here in the Singapore Strait, from these two locations where we're sampling, we see very little spatial variability. We do get a bit of spatial variability in the southwest monsoon. So we tend to have a slight gradient in the water mass composition across, and this is, I think, about 10 to 20 kilometers ish. Okay, you can go to Google Maps and look it up. Okay, now this site up here is in a much more narrowly confined area. There's also degrees of eutrophication going on there, and so the carbonate system up here is quite different to down here. But when you then move inwards into the inner parts of the Johor Strait, it changes quite a lot again. So here, the spatial gradient is quite a lot larger than down here. Now, I think we can get a handle on this because it'll depend quite a lot on the residence time of water. So how well flushed is it by tidal and residual currents? And so if you understand the hydrodynamics, the Danielle here is smiling at me. If you understand the hydrodynamics of your area a bit, then you can get a bit of a handle on that. Now, the other aspect is, of course, what's the biogeochemistry going on in there? So if you're in an area, and I think the Gulf of Thailand might be a nice case, right, where you've got quite a lot of eutrophication, really big plankton blooms, you may have greater heterogeneity. So perhaps their satellite data might be quite a useful way of getting at that, where you can just look at what's your chlorophyll distribution like. So I think it can be quite significant, but I think there are ways in which we can understand it. And you can also, especially if you're considering sensor deployment, you could try to do some field work in the area a bit before, again, with TA, DIC based measurements and try and just map that out. And salinity is a really, really good guide to that. So if your salinity is quite homogeneous, your chlorophyll is fairly homogeneous, then you would expect the carbonate system to not vary too much. Of course, depth variation could then be, Stephen, yeah. So vertical variation could be quite significant there. And how important that is will depend very much on the system and the degree of stratification. Now, down here in the Singapore Strait, because of the fairly strong tidal currents we get, we tend not to see persistent stratification. And we've actually taken measurements all the way down at one point to 70 meters. So there's a hole, I think, somewhere down here. And we basically find the same DIC and TA down at the bottom as we do on top. If you're in a more enclosed, more stratified setting, and I'm sure in Indonesia you will have systems like that, then you could really have some very strong vertical variation. And you might then, maybe it's the most relevant thing is still to concentrate on the surface, but if you can get depth resolution, that would be then great. Yeah. Yeah. Get the physicists on board. I think the millimeter scale, though, is really interesting because as you start approaching sediments and pore waters, and the really small scale stuff, then as you get close to the benthos, that can also matter. And then, your pore water carbonate system will also be set to some degree by what the surrounding seawater is that it's exchanging with. Yeah. Absolutely. So you can have systems that are generating alkalinity as a range of benthic processes, and that can then be important as well. I think at the end, though, there's only so much complexity you can tackle at the same time, right? Somewhere we have to start and start collecting some data. So don't be intimidated by the complexity or the challenges. Okay. Yeah.
Yeah, you just need to jump into the calcium carbons, right? Because
Yeah.
always talking about something he asked you, I would say, he asked me, I focus on like they fall in one of those, so they're interesting out of the are you telling me not, right?
Well, so we'll be syncing with the calcium carbonate as well as with associated organic matter from the cells. So the source sink effect is then dependent on the inorganic carbon to organic carbon ratio. So are you sinking enough organic carbon down with the coccolithophore debris to balance out the CO2 formation that you get from the alkalinity sink? So yes, it can still be a net carbon sink, but it depends on that PIC to POC ratio. So that's defined as the rain ratio, especially in biogeochemical modeling. And right. Yeah, yeah. S-
Yeah, but it's not being solved, right? You know this massive seabed carbon. It's great.
Yeah. So it's you have to think that DIC is more than just CO2. So even if the carbon has ultimately come from the atmosphere, if it's also representing alkalinity, then removing that alkalinity will make the remaining DIC move towards the PCO2, and that then outgasses. It's depressing. It's also quite counterintuitive. So I fully, for those of you who saw this for the first time, I know it's a kind of, what sort of moment. Um, mm, um,
Dioxide and you put it back in CO2, right?
yeah, no, because you're sinking alkalinity with that. So yeah, there's a lot of organic matter outside for lunches there. Or, yeah, sorry. So anybody, any? Oh, okay. I I'm not too sure about. the- So the question is, should we consider coral reefs as carbon neutral?
This is the point about complexity, is that go down the individual components of coral reefs, then they've got impact on growth. As a whole, coral reef has a function, and that is the although process. So it's taken up carbon because it's got all those other things in it as well. And so that as well, talking about it's kind of carbon neutral, I just think it's a really good lost things detail and to get what system that we need to do as a whole.
Yeah, I think it's important to think of coral reefs as not just in terms of what do they do to carbon, right? Coral reefs are important. They're massively under threat. We need more of them. Okay. Uh, the question, I think it becomes complicated though, because it I would not consider them blue carbon because so you can, yeah, 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 yeah. It's, we need to not lose ourselves in just thinking about the CO2 balance. Yeah, 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 yeah. Absolutely. Absolutely. At the same time, I think from if you're trying to track the biogeochemistry, I think it's important also to keep in mind. So a big part of the carbon cycle on reefs, I understand, is that dissolved organic matter gets produced that can then be advected off the reef. So you might find that there's perhaps a net production of organic matter on the reef, but if that gets exported and then remineralized again fairly quickly, that's not. You have to be careful about then thinking of that as a carbon sink. But yeah, but I really think it's important to not just take a blinkered approach and only consider carbon. Okay, so I love coral reefs. I'm all for them. It's simple not. Okay. Okay, thank you very much, and thanks for your participation. And by all means,